Now that you know a little bit about related rates, we're going to get even more complex with our problems. So at the end of this lesson, you'll be able to solve more complex problems using the concept of related rates. Alrighty, one of the ways that we'll end up using related rates is when we have something that involves the Pythagorean theorem. And you will remember the Pythagorean theorem is just a squared plus b squared equals c squared. This will happen when what we draw, the information that we draw, ends up being a right triangle, and we're given some information about all three sides. Then we will apply the Pythagorean theorem. That will be the formula that we'll use instead of area or volume or something like that. So let's take a look at example 1. An airplane is flying at an altitude of 6 miles and passes directly over a radar antenna. You can look at the figure. My radio antenna would be down there somewhere. Okay. When the plane is 10 miles away, so when s equals 10, you'll notice here's my s, so I'm 10 miles away from that radar. The radar detects that the distance is changing at a rate of 240 miles per hour. What is the speed of the plane? So let's just see if we can dig out some information just like we did in our previous examples. I noticed that the airplane is flying at an altitude of 6 miles. So this is a constant 6. It's never not going to be 6, so that's really not information that I need to include in my information that I'm going to write down. Then it says when the plane is 10 miles away, when s equals 10, so this is going to be changing. So we are going to put for right now, we want to find out what's happening when s equals 10. And then it says the radar detects that the distance s is changing at a rate of 240 miles per hour. So it's telling me how fast s is changing with respect to time. So it's telling me that ds dt is equal to 240, and that distance is getting bigger, so it is a positive 240. All right, and then it says, what is the speed of the plane? So basically, if I want to know, it's asking me how fast is the plane traveling, I would like to know how fast is this distance x changing, because that would give me speed. So dx dt is what they're asking me for, and we'll just put a question mark for that from that. Okay, now notice we've got lots of information. The next thing that we need is a formula. And if I look at this, the information does represent itself in the form of a right triangle, and I do notice that I do have information about all three sides. So I'm going to go ahead and use the Pythagorean theorem. So I'm going to have x squared plus 6 squared equals s squared. And I'm just going to clean this up a little bit because I know what 6 squared is. So I have x squared plus 36 is equal to s squared. Okay, now from here, just one comment that I'm going to make. We're not going to put s equals 10 in there right now because that value is changing, so we do want to save that till we're done working with this equation. The next thing that we do want to do with this, though, is to take the derivative. So the derivative of x squared would be 2x, and then don't forget we do need to include dx dt because x is changing with respect to time. Then the derivative of 36, since it's a constant, will just be 0. And then the derivative of s squared will be 2s, and once again it will be ds dt because we're taking the derivative with respect to time. Okay, from here we're just going to try to plug in information that we are given. I notice that we know that s is 10. We know that ds dt is equal to 240. I'm looking for dx dt, and then once again I notice that I do not have any information about x. So time for a side trip. Woohoo! Alright, so over on my side trip, I do know that x squared plus 36 is equal to s squared. I do also know that the problem I'm looking for is when s equals 10, so I can put 10 in for my s. So I've got x squared plus 36 equals 100, x squared equals 64, so I know that my x has to equal 8 at that time. I don't care about the plus or minus because I'm only dealing with positive distances. So I now have found that I can plug 8 in there. So now I'm going to get 2 times 8, which is 16, dx dt equals 2 times 10 times 240 will be 4,800. And now to get dx dt by itself, we'll divide both sides by 16. And when we do that, we will get dx dt is equal to 300. And when I'm looking at units, x, how x is measured in a distance, and that was miles. So miles, and then per what amount of time, and we're talking about hours in this problem, so miles per hour. So that's how fast that plane is traveling. All right, let's find another one. Notice that we've still got triangles based on the example that you can see. Another popular formula we'll end up using is the formula SOHCAHTOA. If you remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, we'll use that when the drawing is a right triangle. This time we'll be looking for an angle, and usually it's the angle of elevation. So you'll notice in that last problem, they said nothing about an angle. This problem, they will say something about an angle. So let's go ahead and read through it. A television camera at ground level is filming the liftoff of a space shuttle that is rising vertically at a rate of 800 feet per second. The camera is 2,000 feet from the launch pad. So you notice we've got this camera hanging over here, 2,000 feet from that launch pad. Find the rate of change in the angle of elevation. You'll notice theta right here is the angle of elevation when the rocket is at 5,000 feet. All right, so let's go ahead and just dig out information. It tells me that the space shuttle is rising vertically at a rate of 800 feet per second. So it's telling me how fast s is changing. So we're going to put ds dt, and it's rising, so it will be a positive 800. And then it says the camera is 2,000 feet from the launch pad. Well, this camera is not moving. It's probably the steady thing, a little bit heavier, so we are good to go. We're not going to put anything because that's a constant. Right, and then it says to find the rate of change in the angle of elevation. So we're looking for how fast is that angle theta changing. So we're going to be looking for d theta dt. And then it says when the rocket is at 5,000 feet. So that would be when s is equal to 5,000. And keep in mind on this, s won't always be 5,000 because the rocket is lifting off. So we're not going to deal with that until after we've taken the derivative. All right, so we've gotten some good information now. Now we need a formula. And I noticed that I have the angle theta. I also have the side opposite, and I also have the side adjacent. So opposite over adjacent is tangent. So I'm going to come over here and write my formula. Tangent theta is equal to s over 2,000. Okay, so we now have a formula that we can actually go ahead and take the derivative of. So implicit, actually there's one thing I'm going to do before I take it. Most people get a little bit stuck when we have s over 2,000. They want to use the product rule, but we don't really need to use the product rule. So I'm going to rewrite that. I'm going to have tangent theta equals, another way of writing s over 2,000 would be 1/2000th s, and that's just an easier way of writing the problem for this situation. Okay, so now we're ready to take the derivative. The derivative of tangent, hopefully you know, is secant squared theta, and we also do need to include the d theta dt because I'm taking the derivative of theta with respect to time. And then on the derivative of the right side, just like if it said 5s here, the derivative would just be 5. So the derivative of 1/2000th s is just going to be 1/2000th, but then I do also need to include ds dt. All right, so now let's see if we can plug in some information. I do know that ds dt is equal to 800. I do know that s is equal to 5,000, but there's not even any place to plug that in. I'm looking for d theta dt, and I also don't have theta. So guess what? Time for a side trip. Okay, with the side trip, I'm going to start off with that beginning formula. Tangent theta equals s over 2,000. We know we're finding our information when s equals 5,000. So I'm going to plug 5,000 in for my s, and then notice 5,000 divided by 2,000 is 5/2. So I would like to figure out where does the tangent theta equal 5/2. And to do that, so if I've got tangent theta equals 5/2, the way that we get rid of tangent theta is we're going to do the inverse tangent to both sides. So we're going to do tangent inverse, and we'll also do tangent inverse on that side. And when we do that, we will get theta equals 1.190. And we should be in radians when we do that. So you'll just hit second tan and then plug in 5/2, and you should get 1.190. So now I can go over here and put in, I know that theta is equal to 1.190. Okay, probably still have some difficulties here because if I'm going to type this in my calculator, we cannot type in secant squared like that. So remember from our chain rule problems, we could rewrite it as secant theta squared, and then we do not have a secant button on our calculator. So we'll type that in as 1 over cosine theta squared d theta dt equals, on this side I still have 1/2000th times 800. Okay, so I know, and I also know my theta is 1.190. So if I plug that in, I'm actually going to keep it like that for just a second. If I wanted to solve for d theta dt, I'm going to divide both sides. I'm going to have 1/2000th times 800. I'm going to end up dividing by whatever answer I get here. So I'm going to put 1 over cosine 1.190 squared. And the reason I did that before actually figuring that out, we'll just get a more accurate answer because we won't have rounding errors. And so when I do that, I end up getting to 3 places, 0.055. And then I need to figure out what theta is measured in. Well, remember, we have our calculator in radians, so it's definitely going to be radians per how fast were things changing. They were changing every second. So it will be 0.055 radians per second. So hopefully now you're familiar with using the Pythagorean theorem and SOHCAHTOA to solve related rates problems.